Hello everyone, I am Dheeraj Madan. Welcome to the 7th lecture of the course on diffusion models. Today we will be learning about noisy conditional score networks. So far in the last few lectures, we have seen some of the algorithms for score matching. Today we will see an algorithm which learns this sort of noisy score models at multiple levels of noise. And then we'll see an Anneal-Langevin dynamics algorithm which will allow us to produce samples from our desired distribution after running the steps with multiple with score networks trained with multiple levels of noise. Okay, so this is all based on a paper by Song and Ermon. I'll discuss the name of the paper soon, and I'll also put up a link to that paper in the description box below. So far what we have seen is that, if we recall, then the idea of this score matching is as follows, that essentially we want to learn a network which can basically determine as the gradients of log probability for us. So essentially we define Sx as gradient over x log pxx. So of course we have some samples xi's which are all sampled from this data distribution pxx, and we want to be able to learn the sort of this distribution pxx. So we what we saw was that getting a normalized distribution coming out from a network is difficult. What we can do is that we can get an unnormalized sort of a distribution, and then if we take the gradient of log, we don't even need the normalization factor. That is what motivated us to get a score network instead. And now what we do is that we define our objective function, which sort of minimizes over theta gradient of x log pxx minus sx theta squared now, right? So here essentially we have an expectation term. So this is the half of the expectation of this sort of quantity, where the expectation is over our data distribution. Now we don't have the gradients of log probabilities for our true sort of data distribution. So essentially the first approach which we saw, which was by Haya-Verinen, so what they showed was that we can write this sort of objective function. So let me just call it L of theta. So L of theta, I can write it as some constant plus half of the expectation x from Ex, the squared norm of Sx theta squared, and then there is another term which corresponds to half of x from Pxx, and then I have trace of the gradient of the score function. So gradient of the score function is actually the Hessian of the log probability distribution, the unnormalized log probability distribution obtained by our model. Okay, so minimizing this we saw was easy. So this was the first approach. The issue with that is that computing this Hessian was difficult, and then the slice score matching algorithm attempted to improve this thing. However, before slice score matching, there was another algorithm by Vincent et al., which, if you recall, what they did was that they had shown that if you have some sort of data distribution pxx, and now what you do is that you perturb this x by adding some noise. So you sample x tilde given x from this distribution px tilde given x, x tilde given x. And now the thing is that if you want to learn a network to model the gradients with respect to x tilde of log sort of p x tilde, then essentially what they showed was that the objective function half of expectation over x tilde coming from p x tilde, the squared norm of gradient with respect to x tilde log of p x tilde, okay, minus the sort of the scores, this squared norm, this equals essentially half of expectation of x from px, okay, x tilde from px tilde given x. So first you sample a data point, and given the data point you add some noise to it. And now instead of taking the gradient of my log probability of my noisy sort of data point, what I do is that I take the gradient with respect to x tilde of log of p x tilde given x. Okay, so this distribution I can take the gradients easily because actually I know x and I know what noise I've added to it, right? So obtaining the two distribution px tilde is hard, but obtaining the distribution px tilde given x is easy. Minus sx tilde theta squared now, right? So this was the denoising objective, right? So here we saw that we can add some noise to it, and now we learn the scores of our noisy distribution. Okay. So here essentially we don't have to overcome the previous problem, but of course the thing is that we are not learning the true scores, we are learning some of the noisy scores. And then we also saw this idea of sliced score matching. Okay, so which essentially took the high variance form, but essentially here what they did was that instead of having norm of s, okay, so essentially instead of minimizing this thing, they minimized the squared length of the projection onto a random vector which comes from some distribution, and the distribution has to satisfy some property. The thing was that the trace thing over here got replaced by v transpose Hessian times v, right? And that made our life simpler, right? Because here we had to backpropagate lesser number of times. So essentially there isn't a half here. I think there's a typo I wrote. So we won't be needing the sliced score matching idea in today's lecture, but we'll be working with the Vincent's idea. So mainly the reference for today's paper. So essentially now what we are going to see is that we are going to extend this Vincent's approach, and we'll try to extend it to work at multiple scales of noise. So whatever we'll be discussing today is from the paper Generative Modeling by Estimating Gradients of Data Distribution. So this is by Song and Ermon. So I'll post a link to this paper in the description box. So firstly, we'll discuss, what are some of the problems which this sliced score matching or any of these score matching algorithms has. So some problems with score matching. So firstly, the first issue is called the manifold hypothesis. So essentially what this says is that, often it happens that the data, it occupies a low dimensional manifold in some, high dimensional space. So for example, the data, it might lie on, some sort of a 2D curved space inside, which is embedded in a 3D space, right? Or it could be, a 1D space which is embedded inside 2D, right? So most of the data could lie on some low dimensional surface or a low dimensional curve in a high dimensional space. So these are just some geometrical examples, but in general it could be any k dimensional sort of a surface in some higher n dimensional space where n is greater than k. Okay, now what is the issue over here? The issue is as follows. Is that if my entire data lies on some sort of a specific surface, then essentially the non-zero probability is only assigned to points which lie on this surface, and outside this surface the probability is going to be 0. Now if I take a directional derivative in any direction, right, which goes outside this plane. So that directional derivative will not be defined, right? It is going to be infinity. So essentially gradient of x log pxx over here is not defined. So this is the first problem which comes up because of this manifold hypothesis. The second issue which we see is that, if we look at the approach, right, so if we look at the original objective, right, in the original score matching paper itself, so if we look at this sort of original objective function, right, so now the claim is that if this objective function, this goes off to 0, then essentially the scores which I have learned, they represent the gradient of the log probability of my true distribution. But is this always true? So in order to prove this, we need to make an assumption that the data distribution is strictly positive throughout, right? It's greater than 0 throughout. So only for the points where it is greater than 0 do we have that sx theta equals gradient of x log pxx. So essentially the issue is that sx theta equals to gradient of x log pxx for all x where pxx is greater than 0, right? So if it isn't true, then essentially it's very difficult to give a handle over the situation, that even if my objective is going off to 0, have I truly learned the gradients or not? So this is the second issue, right? So essentially our whole framework is going to fail if our data is going to lie in this low dimensional manifold, right? So this is one specific issue which comes up due to manifold hypothesis. Now another issue which can come up is when there are some low density regions. So there can be some regions wherein the probability of my data lying in those regions is almost 0. So essentially if I get some IID samples I from 1 to m, then essentially most of these samples will be outside this region, right? Because the probability, the data of the data lying in this region is very small. So essentially the estimate of gradient of x log pxx will not match the true probability in these sort of regions, will not match the, so essentially if we are trying to estimate the scores, then essentially this will not be equal to the learned sort of score model for us, right? Right, for x in this region, this is not going to be true because I haven't seen any samples from this region at all. Right, so this is one issue with low density regions. Another problem which will also come up is that even if you have learned something, right, and now even if you have learned the true scores and now you try to perform this sort of Langevin dynamics, you won't get the correct behavior. Okay. One problem could be, suppose if there is one particular region where the probability is non-zero, another particular region where the probability is non-zero, but in between the probability in this region is almost 0. So now suppose if I am in this space, then essentially if I perform Langevin dynamics, so this is called mixing of Langevin dynamics. So essentially, if I'm in a particular region, then essentially, it might not be possible to reach across this particular sort. So this is a region of low probability. So it might be difficult to tunnel across this region to the other region of high probability. So we have two high probability zones, and in between there is some low probability region. So it might be difficult to transcend this. If you want to look at it in a more mathematical sense, so let's take a hypothetical scenario. Let's take that pxx is actually a mixture of two distribution. Let's say pi times p1x plus 1 minus pi times p2x. where pi is some value which is strictly between 0 and 1, and p1x and p2x are some normalized distribution. Now let's try and okay, so here we are assuming that p1x and p2x have disjoint support. What does it mean is that the regions, the x where p1x is non-zero and the x where p2x is non-zero, so these are completely two different sets, or their intersection is empty. So now this could be, for example, if you take a mixture of Gaussians whose means are really far apart, right, and variances are not that high, then essentially this could be a particular scenario. Okay. Now if I take this gradient of x log pxx, right, so essentially this is going to be gradient of x times log of pi p1x if x lies in support of p1, and gradient of x log of 1 minus pi p2x if x lies in support of p2. So either of these two. And if I take the gradients for the first one, what I'm going to get is that gradient of x log pi plus log p1x, since pi is constant, so this is just going to be gradient of x log of p1x. This is for x in support of p1. And this in the other place, it will be gradient of x log of p2x. So notice the surprising thing, right? So pi has completely vanished. So essentially these scores don't even preserve the information about pi, which is the sort of this is essentially the mixing sort of distribution, right? So how much is the weight for p1 and how much is the weight for p2? We have lost that information completely because of, so this happened because of this disjoint support thing, right? Otherwise this wouldn't have happened. So the solution, to all these problems which we have discussed so far, the manifold hypothesis as well as the problem of having low density regions, so one such solution is given by this particular paper. And the main idea over here is as follows, that essentially we perturb the data with Gaussian noise at multiple scales. Okay. So here, essentially we'll be using this Vincent's approach. Okay, so we'll be using this sort of equality. But here, this px tilde given x, instead of having it at one scale, we'll have it at multiple scales. So if we want to summarize our approach, so here's what we have. So firstly, we are going to perturb data with multiple levels of noise. And then we'll simultaneously estimate the score networks corresponding to all levels of noise. So a single network so S theta x, right, or Sx theta, whatever we want to denote it by. Okay, sorry, this is S theta x and sigma. So sigma is the levels of noise, the different standard deviations for these Gaussian distributions which we'll be looking at. Okay. So let's formally define it. So formally, so we take a sequence of reals in geometric progression. So sigma 1, sigma 2 up to sigma L. So here essentially we have sigma 1 by sigma 2 equals sigma 2 by sigma 3 up to sigma L minus 1 by sigma L, where all of these are greater than 1. So essentially these form a decreasing geometric progression and these are all positive. And essentially what we do is that we essentially define so for every level, right, for every I can consider x, I can consider these conditional distributions x tilde given x, which are distributed as normal distribution with mean x and variance sigma I square I. So I can consider multiple levels for each I, multiple such conditional distributions, and q sigma I x tilde is the marginal on x tilde where x tilde given x comes from the standard normal. So, okay, let me put it more formally. So, essentially, I have defined q, let me call it q sigma I x tilde given x, okay, to be the normal distribution with mean x and variance sigma I square I, and q sigma I x tilde is defined as integral over all x exx times q sigma I x tilde given x, so dnx, right? So essentially I marginalize out x and the distribution over x tilde which I get, this is my q sigma I. So for each I have now multiple distributions over these noisy random vectors x tildes. And now we train a single network as theta x comma sigma, which gives us the gradient of log of q sigma x. So this is what we are going to do. Actually, note that this s theta x comma sigma, I am not actually getting a model distribution and then taking the gradients. In fact, what I am doing is that I am having a network which is directly outputting these scores. Okay. So actually this idea itself was introduced in the sliced score matching paper, and this paper is using that. Now we formally define our noisy conditional score networks. So essentially this Sx theta is called as Sx sigma is called as the noisy conditional score network. And now we'll formally define the objective corresponding to this thing. So learning noisy conditional score networks via score matching. So essentially for a given level of sigma, I can define L theta sigma to be half of the expectation of x coming from px or p data and the expectation of x tilde coming from normal distribution with mean x and variance sigma square I of the quantity as theta x tilde sigma minus gradient with respect to x tilde of log of q sigma x tilde given x. Right, so here I'm taking the gradient of not the marginal but the conditional distribution. Right, actually I should have superscripted it as q sigma x tilde given x, x tilde given x. Okay, so whatever is inside these brackets, these are the actual variable values, and this x tilde given x is a superscript to indicate the distribution I'm defining. Right, so this was the objective which was considered in Vincent et al. Okay, and now let's substitute. Okay, So now let's see what is this exactly. What is the gradient with respect to x tilde of log q sigma x tilde given x. Okay. So this is the gradient with respect to x tilde of log of 1 over root 2 pi sigma to the power d. Let's say we are in d dimension. And then I have minus exponential of minus of x minus x tilde squared over pi sigma square. Okay. So, this log of product is same as, sum of logs. So, this first term will vanish. And log of exponential is going to be minus of x minus x tilde norm square over twice sigma square. If I take the gradient with respect to x tilde, what I'm going to get is that I'm going to get minus of x tilde minus x twice of this thing over twice sigma square. So this is going to be minus of x tilde minus x over sigma square. So this is going to be my gradient. And now if I substitute it, this gives me my function L theta corresponding to sigma as half of expectation of x given by p theta and expectation of x tilde sampled from normal distribution with mean x and variance sigma square I s theta of x tilde sigma minus so this is negative of x tilde minus x over sigma square. So this is going to be plus of x tilde minus x over sigma square. This whole norm square inside the expectation. And now this corresponds to a single sigma, right? So what we are going to do is that we are going to define a combined objective function L theta parameterized by sigma i's I from 1 to L. Okay. So this is defined as 1 over L of sum over I lambda sigma I times L theta sigma I. So essentially each of these losses, that there is a different coefficient corresponding to it called lambda sigma I. Right? So this is the coefficient depending on sigma I. And then I have these losses. So I could have, given unweighted sum, but here this paper actually talks about a weighted sum. And the reason they do it is that we want ultimately we want the order of magnitude of each of these terms in the summation to be equal. Now, if you look at the term L theta sigma, what is the order of magnitude? So its order of magnitude is roughly the squared of the score minus the true score values, right? The true gradients of the log, the conditional log probabilities or log of the conditional probabilities. Now x tilde minus x over sigma squared, the order of magnitude, right? So x tilde minus x, since the standard deviation of x tilde is sigma, so this is order of sigma, and since it's 1 over sigma square, so the order of magnitude of this quantity, right, x tilde minus x over sigma square, the order of magnitude of this quantity is roughly 1 over sigma. And s theta x tilde, since we are trying to equate these two terms, will also be of similar order of magnitude, which is 1 over sigma. So the squared norm is going to be of the order of 1 over sigma square. So we choose lambda sigma I to be sigma I squared. So the reason is that lambda sigma I times L theta sigma I is roughly of same order of magnitude for all I. Okay, so for all I, in order to make it of same order of magnitude, we choose it equal to sigma I squared. Okay, so then the summation, each of the terms are roughly of similar order of magnitude. And now you just train this objective function. So here you have a network which can take in x, it can take in sigma, and then it can produce the score function corresponding to that level of sigma. And once we have trained such a network, we need to be able to sample from a tool, from the distribution we want. Okay? And how do we do that? So essentially, we start from a random point, and then we perform some of these steps of our Langevin dynamics. So we have our algorithm called as the Anir Langevin dynamics. So initially we are going to start from we are going to start these trajectories by sort of taking the score values corresponding to larger sigma, and slowly we'll annihilate it down, right? So we initialize an x naught. Okay, let me just call it x naught tilde, and then from I from 1 to L. So for each of these i's, I'm going to take t steps, capital T steps, okay, with a specific sort of this learning rate or this alpha, which is equal to epsilon times sigma I square by sigma L square. And now I perform capital T steps. So I draw the T-form distribution, normal distribution with mean 0 and unit variance, and then I set xt tilde to be the previous value xt minus 1 tilde plus alpha I by 2 times s theta xt minus 1 tilde sigma I plus root alpha I zi, or root alpha I zt, yes. And this ends the for loop. And after taking these capital T steps, the next initial point which I'll start is with x naught tilde set to xt tilde, right? So this, and then finally I end for and I return xt tilde. Okay, so this is my annealed Langevin dynamics algorithm. So note that now how do I choose the sigma i's? So I need to choose them in such a way such that sigma 1 is large enough to alleviate the problems which we have discussed so far. So what are the issues? Of course, the manifold hypothesis and low density regions. So if I perturb the data with a large enough sigma, then these problems are going to vanish. But sigma L should be small enough so that my data is not perturbed too much, or the distribution does not change too much. So this is how I'm going to choose my sigma i's. Okay, and now if you look at this particular algorithm, okay, so if we look at our diffusion models, right? So over there also we are doing something similar. So if you recall the diffusion model, so over there also we are trying to learn the sort of noise and at different scales, and essentially that we'll see that noise actually corresponds to our score function only. And here essentially if I look at the different time steps of my diffusion model, then you can see that for a larger time step capital T there is more noise added, whereas for a lesser time step there is less noise added. So essentially I'm actually trying to learn these scores only. These scores are corresponding to noise which has been added, and I'm adding noise at multiple scales. So DDPMs, which we saw earlier, are also an instantiation of such a noisy conditional score network. And in fact, even the steps, right, even the later step in order to sample, right, which requires performing a step-by-step sampling at multiple levels, corresponds very closely to this annealed Langevin dynamics algorithm, right? So in the next lecture we'll actually see this sort of connection. So yeah, thanks. Let's again continue our discussion in the next lecture about this sort of correspondence. So we'll finally get to it in the next lecture. After that, I plan to discuss the stochastic differential equation based approach. So yeah, that's it for today. So in the next lecture, we'll also see the classifier guidance also. Yeah, that's also another thing. Classifier guidance and this connection. Okay, so thanks. Yeah, bye.